Hi, welcome to the Euclidean Geometry 101 course. In this chapter, we will start by looking at a special class of plane figures, namely polygons. Let's draw a few. We will take this one and use it to define terminology concerning polygons. A polygon is a plane figure that is delimited by a closed, broken line. So the polygon consists of a finite number of straight line segments. These segments are called the edges or sides of the polygon. They are AB, BC, CD, etc. in the figure. We call the sidelines of a polygon the lines that contain one side of the polygon. So this is an extended side of the polygon. Together, the straight line segments make up the perimeter of the polygon. The vertices of a polygon are the points where two edges meet. So points A, B, C, etc. The diagonals of a polygon are the line segments that can be drawn by connecting two non-consecutive vertices. So like BD, AC. We can define two types of angles in relation to a polygon. The most obvious one are the interior angles, or simply the angles of the polygon. They are the angles formed by two consecutive sides of a polygon and have as condition that points within the angle must be located in the interior of the polygon. That was the obvious one. But every polygon also has exterior angles. They are angles formed by a side of the polygon and the line extended from an adjacent side. There are a couple of ways to classify polygons. We can of course classify them by the number of sides it has. In general, a polygon with n sides is called an n-gon. Polygons with fewer sides have more specific names. Those with 3 sides are called triangles. Those with 4 sides are called quadrilaterals. 5 sides are pentagons, 6 sides are hexagons, and so on. Another classification is whether a polygon has angles that re-enter or not. This is the difference between convex and concave. We will now more precisely define these and make a proposition that will allow to determine whether a polygon is convex or not. A convex polygon has no indentations. That is of course no rigorous definition, but it's helpful. A first rigorous definition can be that a polygon is convex if it contains all the line segments connecting any pair of its points. But there is also a second way to define the concept of a convex polygon. If we consider a straight line in a plane, we can see that the straight line divides the plane in two half planes. If we now consider any sideline of a convex polygon, we see that the polygon will always lie completely in one of the half planes. So, a convex polygon lies always completely in one half plane for each of its sidelines. For instance, the quadrilateral ABCD is convex because it lies completely under AB, left from BC, above CD, and right from DA. The quadrilateral ABDC is not convex. Though it lies completely under AB and above DC, it only lies partially left and right of BD and CA. Remark, a triangle is always convex. So, what do we call a polygon that is not convex? Well, such a polygon, we call it concave. It's now time for another proposition. It's the proposition number 5. A straight line will intersect the perimeter of a convex polygon in no more than 2 points. Let's prove this proposition. So we need to prove that when a line cuts a polygon in more than 2 points, the polygon is not convex. See the straight line D in the figure? It cuts the polygon ABCDEF. Suppose there are 3 intersections, called M, N and P. So we need to prove that the polygon cannot be convex anymore in that case. Imagine having a point that can move on the perimeter of the polygon in clockwise direction. It encounters M, N and P in that order. N lies between M and P, and N is a point of a line segment of the polygon, say AB. So AB can also be seen as a sideline that divides the plane in 2 half planes. The line AB cuts the line D in N, and clearly M lies on the left side of AB and P lies on the right side of AB. Which means that we have 2 points of the perimeter of the polygon that are not situated in the same half plane. And so by definition, the polygon is not convex. Not a corollary in stricto sensu of this proposition, but an important remark can be made about the number of intersections of a straight line with a polygon. The remark is the following: a straight line always intersects the perimeter of a polygon in an even number of points. That's easy to see, because for a point that moves along a straight line in the same direction, we have that for every instance it enters the polygon, there must be an instance that it exits the polygon. So a straight line intersects a convex polygon in 2 points, and a concave polygon is intersected by a straight line in 2n points, where n is a whole number bigger or equal than 1. This concludes our chapter about convex and concave polygons. Next time we will be introducing triangles. If you like this series, consider subscribing to my channel.